Okay, I would like to give some comments on the topic sections at the end of Chapter 1. The first talks about computer algebra systems. There are many computer algebra systems out there. This section mentions several that can be downloaded. A very simple way to do computer algebra is to use Wolfram Alpha. So let me go there and you can see what that looks like. Just to start over, I'll just type in www.wolframalpha.com. Okay, you can see it remembers because it's in my browser, but you can type in the whole name. Now, let's look at a particular problem with Wolfram Alpha. In this case, there's this large system of equations that we'll talk about a little bit later. And you can actually type that directly into the Wolfram Alpha bar. Now, I've already typed it, so I'm going to just copy and paste it from my typing. Alright, so notice how I've done this. It's too long to appear completely, but the first equation on the page was I0 minus I1 minus I2 equals 0. And that's what I typed here. I0 minus I1 minus I2 equals 0. I just typed in the equations that appear on the page as they were written, separated by commas. And if I press equals, it gives me some very strange output. Now, one of the things you need to learn is to try to figure out what the computer is understanding from the output that it gives. Now, from this output, it's clear to me that it doesn't understand that I1 is supposed to be variable I with index 1. It's thinking that the I is the imaginary number and that you should multiply times 1. So what are we going to do? Well, it seems like Wolfram Alpha has trouble with little I and thinking that it's the imaginary I instead of a variable. So I'm just going to go type in the same equations and replace I by X. Right, so I'm going to do that. I've prepared that already, so I'm going to cut and paste that in to the bar here. So now everything is X. I've just typed all the equations one after another, separated by commas, and then I go here and press equals. And now you can see that it has interpreted these as equations. So sometimes it takes a little while to get Mathematica working, but it's well worth the effort to figure out the syntax and how the system understands equations that you put in. But there's a section on accuracy of computations that I'm going to skip. If you take a numerical analysis class, you'll talk about the material in this section. So I'm going to talk instead about analyzing networks. And I want to spend a little time on this because it's a practical application where large systems of equations are used. This diagram looks a little bit daunting, but if you read the text, you can see that this is supposed to represent the electrical system for a car. Right, a car, if you know, has a 12-volt battery in the front. If you've ever had to replace the battery. And the car also has several lights: brake light, parking light, rear light, headlights, and dome light. And these depend on whether certain switches are thrown or not. For instance, if you put on the brakes, that will close this switch, which creates a circuit here. If you have a circuit here, then that means that these lights will go on. The brake lights will go on. Okay. Also, you have a light switch where you can turn on either the parking lights, rear lights, or headlights. And those are controlled by switches on the dashboard. So for instance, in this case, the light switch is for the headlights. Light switch for the headlights is on. and the dimmer is set for high. So in this case, the switch is set so that the high beams will be on. You can see there's a closed circuit here, which allows current to flow, and that means the high beams will be on. These long lines and short lines, the long line indicates the positive side and the short line indicates the negative side. So you know battery has a plus terminal and a minus terminal. So you think of the current as flowing this way, from positive to negative. One of the helpful analogies with current is the water flow analogy. The water flows from higher to lower, and with electric circuits you think of current as flowing from higher potential to lower potential. So here we have a plus. You can think of this as plus 12 volts at the top and 0 volts at the bottom. One thing you should know about car batteries is you can touch the negative terminal without any problem, but you don't want to touch the positive terminal. That's where you'll get the shock. So often the positive terminal is red and the negative terminal is black. The black terminal is safe, the red terminal is not so safe. If you're putting on jumper cables, you should put the jumper cable on the black first and then on the red. Okay, so that's some unnecessary information. Let's go down and look at some of these systems that we may need to solve. Okay. So he explains the two principles involved in solving a circuit. First of all, current passes through the circuit. Current is like water current. You really have to have the same, in this circuit here, the current must be the same everywhere, because like water flowing in the pipe, if there's a certain amount of water flowing in this part of the pipe, the same amount of water has to be flowing in this part of the pipe. Okay, so the current must be everywhere the same in this circuit. In this circuit it's a little bit different. The current flowing here splits into two parts and then rejoins. So the total current, if I cut this circuit at any point, the current that passes this line must be the same as the current that passes this line. But of course the current in this path may be different from the current in this path. So that's one principle, the principle of conservation of current. That's also known as Kirchhoff's current law. So let's see how that works in the particular case. In this diagram, we have I0, which is the current through this part of the wire, which then splits into two parts. I call this current I1 and this current I2. And of course, you'll have I0 back down here because you need the same current there. The point is that this I0 splits into two parts, so the conservation of current gives that I0 equals I1 and plus I2. And whenever you have a split or a junction in the circuit, you're going to have another equation like this that gives a current balance. All right, so that's one source of equations, the current law. And there's going to be an equation for every split. Right? So for instance, we have this split here, we have I0 equals I1 plus I2. That corresponds to this first equation here. Oops, sorry. Give me a minute to recover. That corresponds to this first equation here. Okay. Now here's another split down here. And this says I1 plus I2 is equal to I0. That corresponds to this second equation, down here. Oops, the second equation here. Now notice that these two equations really are the same. When you're using computer algebra to solve systems, you don't really care if you have extra equations because the computer will just mash them together. Okay, so we now have equations for both of the junctures in this circuit. Now, there are additional equations having to do with voltage. So, let's go up here a little bit. Notice that we have 20 volts here. You can think of voltage in our analogy with water, voltage supplies energy. And as the water flows through the pipe, it loses energy. Now, the amount of energy it loses by flowing through this restricted pipe is given by the current times the resistance. Okay? So you can think of the current as starting out with, here we have 20 volts here. So we can think of the current as starting out with 20 volts of energy. Actually, formally in physics, it's not quite energy, but it's related to energy. Okay, so this 20 of energy is going to pass through this part here, and this starts at height 20. Let me write it this way. I have 20 up top, and I have 0 on the bottom. Okay, so this 20 of energy passes through here, and it passes through this section here. By the time it passes through here, it's all the way down at 0. Okay, so it has lost all 20 by passing through this section of pipe. So what does that mean? That means that this 20, the energy it started out with, is equal times to this current I1 times the resistance that it passed through here. Okay, and so that's expressed by this equation here. Okay, the current that passes through this resistor, represented by this squiggly line, is related to the voltage, which is, like I said, it's like the energy, is the energy 20 is equal to this current times the resistance it encounters by passing through this wiggly pipe here. Okay, now that's not the only place that water can flow. Water could also flow in this direction here. Right. So what's happening here? Well, again, we start with energy 20, and we're going through this portion of skinny pipe, and by the end of the time I get out at 0, so I've lost all 20. So that means that the 20 that I started out with should be equal to the energy lost in this pipe, which is given by I2 times the resistance, I2 times 8. All right? So that gives me this second equation here. Okay. Now, in this system of equations, here's another equation here. This equation represents the possibility of water flowing in this circuit here. Okay. Now, if you notice that if water flowed in this circuit here, there's 0 net voltage drop. There's no energy making it go around here. Now, it turns out you don't actually need to include this equation. As I mentioned, if you have extra equations, it's not bad, but you don't actually need to include this equation. Right. So here we have a system of equations, 1, 2, 3, 4 equations, and 3 unknowns. If you do that with Wolfram Alpha or something else, you can find a solution. And that's how you do it. All right, so let's look at another example here. The more complicated example, but really it's the very same principle. We're going to have one equation for each juncture, and we're also going to have one equation for each path that water can follow from top to bottom. Okay. Again, here we have 10 volts, so here we can think of the height as 10 at the top, and by the time it passes through the bottom, it comes down to 0. Okay, so let's first do the equations for the junctures. There's a juncture here where the pipe splits. There's a juncture here where the pipe splits. There's a juncture here where the pipe splits. And there's a juncture here where the pipe comes back together again. Okay, so if we represent using letters, this is a good way to represent it. I0 coming in splits into I1 and I2. Then you have I5 going across, I3 and I4 come back together. So let's consider this juncture here. I0 splits into I1 plus I2, so that gives us I0 equals I1 plus I2. That's this equation here. All right, let's look at this equation, at this juncture here. I1 splits into I3 plus I5. You might worry about, why does the arrow I5 go this way? Why not go the other way? Well, the answer is, it doesn't matter which way you put the arrows as long as you're consistent in the way that you assign the equations with the arrows. The fact that I5 goes to the right here means that I should write I1 equals I3 plus I5, because my I5 arrow is going to the right. So that gives me this second equation here. Okay. This juncture tells me, here I have I5 going in, I2 going in, and I4 going out. So I5 plus I2 equals I4. That gives me this one here. And then finally here I have I3 plus I4 giving me I0, so that gives me this one here. So these are all the current law equations. But now we need the voltage law. Okay. So how can the water go from top to bottom? Well, there are three ways. It can go this way, it can go this way, or it can go across. Now it could also go backward this way, but it really doesn't matter. So we only need to count the three ways that follow the arrows that we see. This way, that goes from I0, from I1 to I3, goes back. The other way is for I0 goes from I2 to I4 and goes back. And finally we have from I1 to I5 to I4 goes down. All right, so let's look at these three equations. Here we had a voltage drop of 10. And here we had resistances of 5. These are the resistances, not the currents. And here we had 10. And here we had 2, and here we had 4. Okay, so if we take the first path that goes through I1 and I3, that tells me 5I1 plus 10I3 is equal to 10. And that's what we've got here. Okay. If I take the second path that goes to the right, I have 2I2 plus 4I4 equals 10. And then if I take the zigzag path, I'm going to have 5I1 plus, I guess this was 50. 5I1 plus 50I5 plus 4I4 is equal to 10. Okay. Whoops. So altogether, I have 1, 2, 3, 4, 5, 6, 7 equations in 6 unknowns, which is good enough. Now, if you don't end up with enough equations, that means that you haven't taken all of the circuits or all of the junctures into account. So you should make sure that you have enough equations. And notice that the equations that have the current balance that come from the nodes are all homogeneous equations. There are no additive constants here. And if you want inhomogeneous equations, you come down here. Actually, the one he did here is a little bit different from the one that I mentioned. He used this circuit here. I used this one here. It turns out to give the same thing. You could have, say, or. In my case, I took 5I1 plus 50I5 plus 4I4 equals 10. So you could do that one instead, and you'll find out that you get the same answer. Plus 50I5 plus 4I4. Sorry, this doesn't work too well. Equals 10. So you could use this one here or this last equation here. Okay. Now, this is used for electrical current, but you actually have similar equations for traffic networks where you have a flow that's conserved. All right. In traffic networks, instead of electric current, you have traffic, you have roads, and you have traffic capacity for each road. And there's some exercises that talk about that as well. Okay, that's it.